Hello everyone, welcome to my videos on elementary differential equations. This is an extra video for chapter 7 on the topic of system of two nonlinear differential equations. Here in this extra video, we will go through in some detail an example in population dynamics, namely the two competing species model, and take a closer look at possible solutions. Okay, let's get started. Let's review the model for two competing species. So suppose now two species live in an enclosed environment and they're competing for natural resource. And now we let X and Y be the population. We assume that if a species living alone without the other one competing with it, then the population follows the logistic equation. This means the following. If, say, y is 0, x lives alone, then it has the logistic equation that can describe the population with coefficient a1 and b1. And we know that here the a1 will be the growth rate. And then when the population reaches the number a1 over b1 such that this rate becomes 0, then it reaches the, we call it the habitat's capacity. Okay, so that's for y equals 0. Now, a similar scenario for the case where x is 0 and the species y lives by itself, and it follows this logistic equation with the coefficients a2, b2. Let's say they are all positive. And with a similar argument, we know a2 will be the growth rate, and a2 over b2 will be the capacity of the habitat. And now consider that the two species are competing, then each one will have a negative effect to the other. And then we modify the system into the following. So for the equation for x, we add a negative term. The growth rate will decrease if y is present. And how much it decreases is with this proportional to the y population density times a constant c1. And the same thing for the population for y. It will have a negative growth term, including x, multiplied by a constant c2. Okay. So one important thing here is that all these constants, the ai's and the bi's and the ci's, they are positive constants. Therefore, the sign we put in front actually denotes the sign of that term. Okay, now let's find the critical points for this system. So we know that for the first equation, we have x equals 0, or this factor is 0. And for the second equation, we have y equals 0, or this factor is 0. And then we can make 4 combinations. And the first one will be take this one with this one, then we get 0, 0. And the second would be take this one combined with this, which will give us y will be a2 over b2. And the third one will be taking this one and that one, then we have y is 0, x is a1 over b1. And then possibly there is one more, that is where we have this factor 0 and this factor 0, which we can rewrite here. We see that these are two linear equations, and we have two unknowns, x and y. Okay, so let's take a look at the last critical point, number 4. It needs to be a solution for this linear system of two equations. And furthermore, we are only interested in the solutions that lies in the first quadrant, that is where x is bigger than 0 and y is bigger than 0. Okay, so we know how to solve such a system theoretically. So if the determinant b1, b2 minus c1, c2 is not 0, then we know that there is a one and only solution which we can write out theoretically. It takes this form, the solution for x and the solution for y. Here we're just writing it out. We don't know if these two numbers are positive or not. Okay, so on the other hand, if b1, b2 minus c1, c2 equals 0, then there might be no solutions or infinitely many, and again that would depend on the other values. Here will be for the value a1 and a2. Okay, and let's recall the Jacobi matrix for the system here. And the Jacobi matrix will be this one differentiating in x, and if we work out, we'll get that. And then you differentiate this in y, you get negative c1 times x, which is here. And the second row will be differentiating this one in x, you get negative c2 times y, which is here. And then the last was this one differentiate in y, which you can use the product rule and then clean it up, and you get this expression. Okay, so we see that the critical points and how many of them we have in the first quadrant will depend on the value of the coefficients. So, and different sets of these coefficient constants would lead to very different dynamics of the two populations. Okay, so now let's look at a somewhat different and more geometric or intuitive way of viewing the dynamics of the system that's given here. Let's look at where this factor and this factor becomes 0. So when along what line or what path in the phase portrait will this one be 0? Well, that is exactly the solution of this equation equals 0. And we see that A1, B1, C1 are constant, so this becomes a straight line. And then also here, equals 0 is also a straight line. So let's call this line 1, and this is line 2. So geometrically, when both of the equations are satisfied, then the solution becomes the coordinate of the intersection point of these two straight lines in the first quadrant, if it shall happen. And that will give us the fourth critical point. Let's take a look at the behavior of the solution along these two lines or nearby. So look at line along line L1, it's a factor for x prime. Along line L1, this factor is 0, so x prime is 0. We'll have that. And then we see that above L1, which means y is bigger than this x prime, this value here decreases, and then we get x prime less than 0. Okay, and below L1, y gets smaller, and then this term becomes positive, and then x prime is bigger than 0. So in terms of a directional field, then x prime is 0, then you have a vertical direction, and x prime is bigger than 0, then your arrow will point towards the right, and this means your arrows will point to the left. Okay, and similar analysis can be applied to the line L2. Along the line L2, we know y prime is 0. And above L2, x becomes bigger, then we know the y prime becomes less than 0. And then below L2, x is smaller, then this term becomes positive, so y prime is bigger than 0. Okay, so solely looking at the configuration of these two lines in the first quadrant and their relative position to each other, we see that there are four possible configurations. And one group is that these two lines never intersect in the first quadrant, and then line 1 could lie above line 2, or line 1 could lie below line 2. So two cases there. And then in the case where these two do intersect in the first quadrant, then there are also two configurations, like line 1 is first below line 2, and then after intersection they switch the position, and the other way is line 1 is initially above line 2, and then after intersection they switch. Okay, let's take a closer look at all these four configurations. Case A is the case where line 2 lies above line 1 completely, and they do not intersect in the first quadrant. And then we see that the system will just have three critical points. One is at the origin, and one is here where line 1 intersects with the x-axis. Another is here where line 2 intersects with y. And there is not the number 4 critical point. Okay, let's look at the direction where the solution moves. So along line 1, we know x prime is 0, so it will move vertically in the y direction. So how do you determine the direction of the arrow? Does it point up or point down? Well, we can look at the relative position of L1 with L2. We see now L1 is below L2. So from the discussion on the previous slide, we know below line L2, y prime is bigger than 0, and therefore we have the arrow pointing upward. And a similar analysis can be done for solution along the line L2. Here we know y prime is 0, so your arrows will be horizontal. So does it go towards the left or towards the right? Meaning, is y prime less than 0 or bigger than 0? Well, we see that L2 lies above L1, and therefore the y prime is less than 0, so the arrows point to the left. Okay, so now recall that the solution near this critical point 0, 0, it's unstable, and the solutions will go out. So we have the arrow here going out and the arrow here going out. Okay, and then the solution above this one, we see that it goes down, and then the solution bigger than this one, we see it also goes back. And nearby solution would be the following. So if a solution goes this way up, then it comes somewhere from the origin, right? Once it enters the region between, then it gets affected by this arrow that it's pointing to the negative side. So it will eventually go to the left and approach that point. Okay, and then if, let's say you're here, you come out and you're here, and then this will make you cross, and then you see, and over there the arrow will make you go up there. Okay, so finally, if you are here, well, you know the solution will come, and then it will follow this, and then it will eventually get to that. So all solution will go towards this critical point. Okay, so here I provide a graph done with MATLAB, much better than my wiggly drawing with an Apple Pencil. So we can add the arrows from our discussion. So we see that all the solutions will eventually all approach this critical point along the y-axis. So what does it mean? Well, this is a asymptotically stable critical point. And then it also means that in the long run, the population of species X will die out, and in the end, only one species can survive in the long run. Now let's look at case B. It's a counterpart of case A, where now L2 lies below L1. So again, there are 3 critical points, one at the origin, one here on the y-axis, and then one here on the x-axis. Okay, and along L1, we know x prime is 0, and then y prime is less than 0 because it's above L2. And similarly, along the L2, we know y prime is 0, so it's horizontal. And then because it's below L1, then we know x prime is bigger than 0. Therefore, the arrow points to the right. And we see that this is a counterpart. It's kind of a flip the row of x and y from the previous example. We can visualize solutions that comes up and then bend, and then it will go towards that point because everything goes down there. All right, and if you are above here, and you will go to that point as well. So this solution here is an attractor that all solutions goes there eventually. Okay, so here is a plot done in MATLAB by some numerical simulation with constants that end up in this graph. And we see that we can add the arrows. We know the solution will all go to that point. And then here it will also all go in that direction. Okay, so this becomes an asymptotically stable equilibrium. So the meaning would be that species X will exist alone, and this species Y will die out eventually. Now let's look at case C, where L1 crosses L2, and in the case that L2 is above L1 for small x value, so L2 is above L1, but then they cross, and after they cross, then L2 is below L1. Okay, and the point they cross becomes the 4th critical point. There is another critical point here, and we know that let's say along x1, we know the vector field, the directional field, is a vertical line. To determine the direction, we see that on the left of the critical point, L1 is below L2, so y prime is bigger than 0, so I have arrow going up. And on the right of the critical point, then y prime is the line L1 is above the line L2, so y prime is less than 0, so we have arrow pointing down. Okay. And similarly for along line L2, we'll have horizontal directional field. And to determine which direction they actually point, we see that on the left of the critical point, L2 is above L1, therefore x prime will be less than 0, and it goes to the left. And on the right, L2 is less than L1, then x prime is bigger than 0, and the arrow points to the right. Okay, so now we see that in a neighborhood of this critical point, solutions actually would go away. So imagine some solution over here. It would come from the origin, and then it would go up to that point. Okay, and the solution down here would go towards this point, and then solution nearby here will go towards this point, and solution nearby here will go towards that point. And in particular, there would exist a point that the solutions would actually go here and the solution will actually go here. But it's very sensitive to small perturbations. If you perturb it a little bit, if it shall fall to the left side, then it will go to that one. And if it shall fall to the right side, and it will go to that one. So this solution in the middle is called a separatress, and it separates the region into two parts. Any solution lies on its left will eventually be attracted to this critical point, and then any point on the right of that will eventually have solution approaching this critical point. Okay, so here is a graph generated in MATLAB with some number, that coefficient number that falls into this case, and we see that we can add arrows. So here solution all goes in, and then here the solution will go this way, and they will end up in this critical point. And down here the solution goes in, and here it goes to the right, and it will end up in here. Okay, and we see that it's very hard to find this solution of the separatress because it's extremely sensitive to perturbations. But we can see that there is somewhere a special solution, very touchy, that separates the behavior on the left and on the right into two different types of behavior. Okay, so whichever side you end up with, the final result would be good news for one species and bad news for the other one, because these two critical points means that here it means y die out, x exists alone, and here is x dies out and the y exists alone. Okay, so such critical points are called locally stable. They are called local attractors for nearby solutions. And very often one also classify the basin of attraction here that will be cut by this separatress, and then over this region this is the attractor, and the region below this is the attractor. Okay, so far for all the cases we have seen, there is no coexistence. It seems like coexisting is very hard. But we have one more case. Do you think that case will be the one with coexistence? Let's look. Okay, case D. That is the case L1 crosses L2 in the first quadrant, but with different relative position. That is, on the left, L1 is above L2, and on the right of the critical point, L1 is below L2. Okay, so we have 4 critical points, and let's look at the direction of the vector field, how the solution flows. Along x1, we have vertical lines, and then on the left, it's above L2, so y prime is less than 0. We have arrow pointing down, and then down here, y prime will be bigger than 0. We have the arrow pointing up. And then along L2, we have horizontal arrows. And then on the left, L2 is less than L1. Then you point to the right, x prime is bigger than 0. And then over here, x prime will be less than 0. So you point to the left. Okay, so how do the solution nearby behave? Well, we see that if some solution is in this area and it's restricted between this area and pointing upward, and it will eventually go to that critical point. And also our solutions over here will all come down and go to that point. And then solution down here will come up and then be attracted to the critical point number 4. And then solution here is the same. Everything point in there. And then solution over here, you will come down, but then that's the only attractor that attracts you. and then solution here, you will come down and you will be attracted to that point. So it seems like everything is being attracted to the last critical point. Okay, so here I present a computer-generated graph, much nicer, and we see that here's the critical point, and we see that all solutions are attracted to it. And let's add the arrows. So all these will go down and to the left, and this will go down and then will bend, and then down here all the solutions will go up. And everything goes towards the critical point. So if you have an initial condition that is strictly in the first quadrant, that x is bigger than 0 and y is bigger than 0, then in this case we have a stable asymptotic equilibrium, which is the coexisting of the two species here right at the middle. Okay, and that's the only case among the 4 where coexisting is possible. Okay, so that's all the cases, and that's all I plan to say on that. Just to show you that the complexity of such a simple model with only 2 competing species. Okay, so hope you enjoy this, and next time we'll move to chapter 8 on a new topic of Fourier series. Okay, I hope you enjoyed this one. I'll see you next time.